In this lecture, we are going to look at a very simple plug-and-play example of using TensorFlow for multi-class classification. Now, a lot of beginner students misunderstand the purpose of this lecture, so I think it's important to talk about that first. As you hopefully know by now, TensorFlow is not one of the main learning goals for this course. In fact, TensorFlow is completely unnecessary for this course in relation to the main topics. If you don't know what the main topics are, I think this would be a good time to revisit the course description. As a hint, one of the major topics of this course is backpropagation. The reason why this TensorFlow example is useful is not because you're learning TensorFlow itself. It is because it highlights and complements what you have already learned. I already have separate courses on modern deep learning libraries, and ones that focus specifically on TensorFlow and PyTorch. So it should be obvious that this course is not simply a replica of those courses. So what is the point of this lecture? Remember that you are here to learn backpropagation. If you learn the topics of this course successfully, what should you have learned? First, you should have learned that backpropagation is hard. It's definitely not easy to derive all those equations. However, you should have also learned that backpropagation is mechanical. That is, it follows a simple set of predefined rules. So one obvious question is, can I program those rules into a computer instead of deriving them by hand? 3. As your neural networks get bigger and bigger, the equations become more and more complex. So again, another reason why you might want to automate this process. If you imagine building a 100-layer neural network, it would be unreasonable to derive all the updates yourself. However, if you're smart about the recursive properties of backpropagation, doing this in a computer becomes manageable. 4. As you work with larger and larger datasets, you will come to realize that backpropagation is quite slow. In modern times, we have specialized hardware that can make these calculations faster. However, Python and NumPy are not built to take advantage of this hardware. Okay, so that brings us to the TensorFlow example. How does this TensorFlow example complement what we learned in this course and what we have just discussed? Firstly, it takes care of this backpropagation business. As mentioned previously, all the rules of backpropagation are mechanical and can therefore be programmed. In modern machine learning, we call this process automatic differentiation. That is, the TensorFlow library automatically derives all the update rules and the gradients for training your neural network. It does so by creating what is called a computational graph. If you've ever studied algorithms and data structures as part of your computer science degree, then you should be familiar with the idea of graphs. Basically, graphs are useful data structures that help us abstract away the components of the neural network. They allow us to conveniently define both the forward propagation and backpropagation steps recursively. So one thing you should look out for in the following TensorFlow example is that unlike regular Python, there are 2 steps to building and running a neural network. Step 1 is to build the computational graph. When doing so, you will realize that we are defining how the neural network is connected, but at this time we do not pass in any data and we do not do any computations. If this is the first time you've seen something like this, it can be quite strange. Step number 2 is to actually pass your data into the neural network to do both training and prediction. This only happens after your computational graph is built. Alright, so that's the first interesting detail that you want to notice about TensorFlow. The second important point is that, as mentioned previously, neural networks are slow. We have specialized hardware called GPUs, which can speed up the calculations inside a neural network. Python and NumPy do not have the capability to take advantage of GPUs on their own, but TensorFlow does. So these are 2 major ways that TensorFlow complements what you learned in this course and improved upon the existing ways of doing things. Number 1, it implements automatic differentiation, and number 2, it knows how to take advantage of specialized hardware. As a side note, I should mention, in case it's not clear, that this is not specific to only TensorFlow. In fact, TensorFlow was not even the first library to do this. The first Python library to do this and gain significant traction was called Theano. Therefore, we could have just as easily done this lecture in Theano. However, it was clear to me when I made this course that most people did not know about Theano, whereas they did know about TensorFlow. Ultimately, they accomplished the same thing. TensorFlow was heavily inspired by Theano, as were a few other libraries. Today we have even more libraries such as PyTorch, MXNet, and JAX. Interestingly, JAX, which is the newest of these, was also created at Google and looks more like Theano than TensorFlow. Now, sometimes beginners will ask me, why not do this example in TensorFlow 2 or Keras? The answer to this question should be clear, but just in case it isn't. TensorFlow 2, or equivalently Keras, does not highlight the previously discussed principles. In fact, the whole purpose of Keras was to hide these implementation details. So by using TensorFlow 2 or Keras, you are missing out on the whole purpose of this lecture, which is to see how modern deep learning libraries implement some of the ideas we previously discussed. Furthermore, if you are interested in learning TensorFlow 2, let me remind you that this course is not about TensorFlow 2. I have a course on TensorFlow 2, but this is not it. So if you came here to learn TensorFlow 2, you are definitely in the wrong place. There is a place, but this is not it. As you are at least several hours into this course by now, hopefully you've realized this. This lecture could have been done in TensorFlow or Theano or even PyTorch, and the result would have been the same. You are not watching this lecture for syntactical details. You are watching this lecture for conceptual understanding. Okay, so that being said, let's get to the code. Let's start by importing TensorFlow, NumPy, and Matplotlib. Remember, this is TensorFlow 1, so if you actually want to run this code, you should create a virtual environment and install TensorFlow 1. Of course, that's not really necessary since the whole purpose of this lecture is to understand the principles and not actually run the code. You already know what the code is going to do because I'm going to show you. There's not much point in you running the code simply to get the same output because you're already going to see it. Now, the first part of this code is going to be exactly the same as we saw earlier in the course. So I'm just going to copy and paste that part from earlier. Now, this makes perfect sense. We want to replicate our previous example, but switch out our NumPy implementation with TensorFlow. We want to show that either way you do it, you still get a neural network, and they are still the same kind of neural network doing all the same computations. Okay, so we have 3 Gaussian clouds, where each Gaussian cloud is a different class. We have 500 points in each class. The Gaussians are centered at 0, -2, +2, +2, and -2, +2. We're going to do a scatter plot, just in case you forgot what the data looks like. And we're going to create indicator variables for the targets. Okay, so after this, we have new code. So TensorFlow does not use regular NumPy arrays. Instead, it uses TensorFlow variables. In this function, we are going to initialize some weights, also known as parameters. We have one argument to this function, which is the shape of the weights. Inside this function, we want to wrap the return value in a tf.variable object. These are used to encapsulate model parameters. In other words, parameters that you would want to be trained during backpropagation. Inside the TensorFlow variable, we're going to call tf.randomNormal. This works very similarly to NumPy's randomNormal function, except it returns a TensorFlow object instead of a NumPy array. We'll pass in the shape to specify the shape, and we'll also set the standard deviation to 0.01. Next, we're going to write a function that describes how the neural network should do forward propagation. Note that I did not say that this function actually performs the forward propagation. This is an important distinction. Okay, so this function takes in some data x, as well as a set of parameters w1, b1, w2, b2. And now we're going to define how our neural network computes its output. First, we'll calculate the hidden layer. This will use TensorFlow's version of the sigmoid function. Inside that, we use TensorFlow's version of matrix multiplication, which uses the function tf.matmul. Unfortunately, NumPy's dot function does not appear in TensorFlow, although it does appear in Theano. So in some ways, Theano is a nicer library because these functions map one-to-one with NumPy. But as you can see, the general pattern is the same. We take x, multiply it with w1, and add the bias b1, and pass that into the sigmoid to get z. In the next step, we calculate the output by taking z, multiplying that by w2, and adding b2. Note that we do not apply the final softmax at this time. The reason for this is numerical stability. As you recall, the softmax function requires doing an exponential. Exponentials can make numbers very big, so big that they do not fit into your computer's memory in the space that has been allocated for them. TensorFlow does a smart thing where it combines the softmax with the loss function, which you will see later. Intuitively, you know that the loss function contains a log. Therefore, if we combine something that does an exponential and something that does a log, they will cancel each other out in terms of scaling. Note that this intermediate output, right before we would have applied the softmax, is called the logit. Okay, so the next step is to create what are called TensorFlow placeholders. These are what represent our data. Notice one important thing, which is that this doesn't actually use any of our data. Our data is inside variables called x and y, which we defined earlier. Remember that all we are doing at this time is creating a computational graph. We are only telling TensorFlow how to compute these things without actually doing any computation. So all we've passed into the placeholder is just some basic information. First, we say that the type of data we're going to pass in is float32. Second, we say that the shape of the data that we're going to pass in is none by d. The reason the first value is none is because we want to be able to pass in data of different sizes. So if we want to pass in a one sample, we can pass in a one sample. That might be when we want to make a prediction. If we want to pass in n samples, then we can pass in n samples. That might be when we want to do training. Okay, so next, we're going to create another variable for the targets, tfy. As expected, these will have the shape none by k. Okay, so next, we're going to create all the parameters for our model using our initWeights function. That's w1, b1, w2, and b2. Okay, so hopefully you're familiar with all these shapes from earlier in the course. W1 is d by m, b1 is just m, w2 is m by k, and b2 is just k. Next, we can use our forward function to get the output of our neural network. We'll call that logits. It takes in tfx, the placeholder, along with the TensorFlow parameters that we just created. Note again that we have so far done zero computation. We're only saying how the neural network should compute the logits. We have not yet passed in any data. Next, we're going to define our cost or loss function. This is going to be wrapped in a function called tf.reduceMean. Why? Because the loss function we're going to call computes the loss function per sample. So that's why we want to take them all together and calculate the mean. So inside that, we have the loss function, which is a very long name, softmax cross entropy with logits. As you recall, the logits are what we got out of the forward function. So for this function, we're going to pass in the labels, which are represented by the placeholder, tfy, and the logits. Next, let's remember that in TensorFlow, you do not have to do any backpropagation yourself. TensorFlow does all of that automatically. We can set up the training process by creating an optimizer. So we call tf.gradientDescent_optimizer, passing in a learning rate of 0.05. When we get our optimizer, we call the minimize function, passing in the cost we defined earlier. Hopefully that makes sense. We want our gradient descent optimizer to minimize the cost. Okay, but remember, this function hasn't actually done any computation so far. We've only stated how to do the computations later when we actually do them. Okay, so next, we're going to define a predict operation. This will take in the logits from our model and return to us the predicted class. Basically, instead of NumPy's argmax, we use TensorFlow's argmax. So this one should be pretty simple. Again, notice that no computation is being done. We're just saying how it should be done. Finally, the last step is to actually do all the computations. We spent all this time setting up our computational graph, so now it's time to use it. The first thing we have to do here is just some boilerplate code. A lot of beginners often get uncomfortable about sessions. They demand to know what a session is. They truly believe that it's an integral part of deep learning. I'm going to tell you right now that this is false. Sessions have nothing to do with deep learning. They are just an implementation detail of TensorFlow 1. In fact, they do not exist in any other deep learning library. In fact, in TensorFlow 2, Google has removed sessions. So sessions are not related to deep learning. They were just an API that Google wanted to use early on in their first version of TensorFlow. Okay, so this is just boilerplate code. You do it because it has to be done. When we call global variables initializer, this is going to actually give our parameters values. If you recall, we previously only defined how those parameters should be initialized. Now we are going to give them actual values when we call session.run init. Next, we enter our main training loop, which will go for 1,000 iterations. Inside the training loop, we're going to do one backpropagation step. So we call session.run and pass in a train op. As you recall, this is what we got back earlier from our optimizer. It is also at this point that we actually pass in our data. You can see that we do this by using the argument feedDict. This will be a dictionary where the key is the placeholder variable we defined earlier and the actual value for the placeholder, which is a NumPy array. Okay, so the key is the placeholder. The value is the actual NumPy array, which holds the data. This is going to run one step of backpropagation, just like you learned how to write earlier. But notice how easy this is. You don't need to derive any gradients yourself, nor vectorize your computations. All you have to do is run this function. The next step is to get our predictions. As you recall, this is represented by the TensorFlow variable predictOp. So again, we use session.run, passing in the thing we want to compute. And again, we have our feedDict to pass in the data. Note that this time, session.run returns a value. We'll call this pred. Note that pred is not a TensorFlow variable, but rather a NumPy array. So the interface to the session is NumPy arrays, even though internally it's using TensorFlow variables. We pass in NumPy arrays, and we get back NumPy arrays. Next, we check if the iteration number is a multiple of 100. If it is, we'll print the accuracy of our model. We use y equals pred, which will return true for each element in y that is equal to pred, and false otherwise. Therefore, this returns an array of length n containing all trues and falses. Since in Python true equals 1 and false equals 0, we can use the mean function to calculate the accuracy. Okay, so let's run this and see what we get. Alright, and so our model trains to a high accuracy, as expected. Okay, so to conclude this lecture, it's worth noting once again that the purpose of this lecture is not to teach you TensorFlow, but rather to teach you the concepts behind modern deep learning libraries in general. TensorFlow is merely one example out of many. The purpose is to observe for yourself the idea behind creating a computational graph and automatic differentiation. You've observed that the whole process happens in 2 steps, rather than all at once like in regular Python and NumPy. First, we have to create the graph to tell TensorFlow how things are to be computed. Then we use the session to actually compute those things. Hey guys, and welcome back to this class. Deep Learning in Python Part 1. In this lecture, we're going to do a visual representation of what a neural network is learning. Now, TensorFlow has created a really cool tool for this. You want to go to playground.tensorflow.org and you can basically see the exact same thing that I have here. Now you see guys, the donut and XOR problems are actually very important because even the guys at Google say so. So first what we're going to do is we're going to look at the famous donut problem. And we're just going to do logistic regression. So that's 0 hidden layers. So we know that If we just have x1 and x2, we can't learn the solution for the donut. So you see our test loss and our training loss is about 0.5. But we already know that if we add the radius to this, we can solve this problem. Really, the radius is the only discriminating feature. So the radius would be x1 squared plus x2 squared and take the square root. The square root is not needed, of course, so we really just need x1 squared and x2 squared. And we can get that by doing x1 squared separately and x2 squared separately. So if we train this model, okay, we see that the test loss is now very close to 0, although the visualization did not refresh. Okay, so the visualization is a little bit buggy, but if you move your mouse around a little bit, you can get it to work. Okay, so now let's try the XOR problem. So this is XOR. We know that just passing in x1 and x2, you will not be able to solve this problem. So we again get something around 0.5 loss. Okay, and now we know that by adding the x1, x2 feature, we can solve this problem. It's pretty much exactly the same shape as the input. So let's train this model. Okay, and we can see that our loss goes down to about 0. And it's only depending on x1, x2. So the color and the width of this line shows you how strong that signal is. Okay, so the next thing we want to do is we don't want to use these extra features. We want the neural network to learn these features. So let's go and add one hidden layer. Okay, and let's try to train this and see if the neural network can learn the pattern. Okay, we see that with 2 neurons, it does okay. See the visualization has updated itself, so these are the boundaries it has learned. So the test loss and the training loss are not quite as good as we can get. But we can add more neurons in the hidden layer with this button. Okay, you train it again. Okay, so with 3 neurons, it's still not that great. So let's try to add one more. All right, so you see that with 4 neurons, it gets much better at learning this pattern. So now let's go back to the donut and do the same thing. So let's start it with 2 neurons and see what we get. All right, so not super great. Now let's try 3 neurons. Okay, so it still seems to be having some trouble. Now let's add one more neuron. Okay, so 4 neurons seems to be the magic number for learning these patterns. Notice that you can also make a deeper network. You can add more hidden layers and more neurons if you want. You can also change the learning rate. You can change the activation function. You can add a regularization if you want. And you could even do different types of problems like classification or regression. So now one harder problem we didn't talk about was the spiral problem. You'll see that it definitely won't be able to learn this based on just x1 and x2. So you might think that by adding sine x1 and sine x2, because these are periodic functions, that they might be able to learn this. See, but even those are not good features for learning this pattern. We could even try adding all the features. See if it can learn this pattern. Right, so it's a little shaky and it levels out at 0.5 error. We can try changing the activation, which doesn't really matter because there's no hidden layer right now. But now we can add more hidden layers. So let's go with 8, okay, and let's use all the features and see if the neural network can learn the spiral. Okay, so it's doing a pretty good job now. Now, if you look at the neurons, you can hover over them to see what distinct pattern each neuron is learning. So it's a pretty complex shape, right? And the total of it is to learn the actual pattern. Now, what would be ideal for us is if we didn't have to create these manual features, right? So typically all we have is the raw data, and we're not going to square everything and do interaction effects and sines and cosines and things like that. That's what statisticians do. So we would like to have just x1 and x2, and the neural network can learn these things for us. But you see that with one layer and 8 neurons in that layer, it doesn't do a very good job. All right, so what we can try to do is add more layers. So the playground lets us add 6 hidden layers, and we can just add as many neurons as we can. So it lets us go up to 8. So we'll add 8 neurons in each hidden layer, and we'll have 6 hidden layers. So let's see if the neural network can learn this. So you see it's learning much more slowly than in the previous examples. So this is a much harder problem. And it also seems to level out around here. So let's try a different activation function, the rel-u, and see how well it can do. All right, so there's still some shakiness, but it's still going down overall. Okay, now after a while, it seems to have learned a very crooked spiral. It's interesting that we were able to do this with the rel-u, but we were not able to do this with the tan-h. So as a challenge, I would ask you guys to see what other configurations you can come up with to solve the spiral problem. Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. So this is the official end of the course. After this, there is no more theoretical material, and it's just practice on the concepts that you already know. Let's review what you learned in this course. I took you from logistic regression to building a neural network out of individual logistic units. We then took logistic regression for binary classification and extended it with softmax for classifying an arbitrary number of classes. We talked about how to derive the gradient for backpropagation from first principles, and remember, what's most important isn't that you watched me do it, but that you're able to do it on your own. If you can't, you should practice until you can. We also covered practical issues surrounding neural networks, like how to choose the learning rate, the regularization penalty, the number of hidden units, and the number of hidden layers. I showed you how to do cross-validation so that you can properly decide which model is better. So what else is there to learn about neural networks? We've just scratched the surface, but the fundamentals are very important. Without the knowledge and experience you learn in this class, you won't be able to tackle these other subjects. Convolutional neural networks are a state-of-the-art method for classifying images. Unlike this course, we'll treat data as actual images instead of turning everything into flat vectors. Neural networks are also state-of-the-art at NLP, or natural language processing. They allow us to model the dependencies between the words in a sentence and to represent words as numerical vectors, since that's what neural networks work on. One popular example of this is word2vec. This allows us to perform operations like the famous king minus man plus woman equals queen. Next we have recurrent neural networks. These are networks that incorporate a time element. They include feedback connections, and they have been historically hard to train, but recent developments have moved us forward. We also have more modern training methods than pure backpropagation. Research has found that by pre-training with models like restricted Boltzmann machines and autoencoders, we can improve training. Dropout and drop connect are new ways to regularize a neural network and are alternatives to the usual L1 and L2 regularization that we usually use. Finally, there's reinforcement learning, which is a topic that is less frequently talked about when it comes to deep learning, but at the same time has achieved a lot. This is the technology behind Google's AlphaGo. So where do we go from here? Well, there's a lot more to learn when it comes to deep learning, and there are courses right here on Udemy that will teach you the stuff I talked about on the last slide. You should be able to find these courses easily when you click on my profile. Next, you'll want to visit my site, lazyprogrammer.me, and make sure you sign up for the newsletter. I give out coupons for my Udemy courses and write free machine learning articles all the time. It's the best way to stay up to date on what I'm doing and free learning resources I've released to help you become even better at deep learning. Don't forget to review this course and tell me what you liked and didn't like. I've updated this course more than a handful of times since its inception, and it's all thanks to feedback from you guys. Finally, follow me on Twitter and like my Facebook page. This is yet another way to make sure you're first in line for early bird specials whenever I release a course and give out coupons. Lastly, I would like to thank you for taking this course. Hey guys, and welcome back to Deep Learning in Python Part 1. I made this lecture as an extra lecture a few months after starting this course, because I realized some people were taking this course and didn't realize how applicable the stuff they learned is. So to begin, I know what a lot of you guys have as your end goal is understanding the latest and greatest neural network and deep learning architectures. Convolutional neural networks and recurrent neural networks like LSTMs come to mind. And you might ask, Well, all I learned in this class was how to take derivatives. So how does that teach me about convolutional neural networks and LSTMs? Well, I'm glad you asked. In the next few slides, I'm going to talk about some newer and very popular deep learning developments and how the skills you learn in this class will help. First, let's go all the way back to logistic regression. Remember that there are two functions for these supervised types of machine learning problems: prediction and training. For logistic regression, the output is y equals a nonlinearity of w times x. So that's how you do prediction. For training, what do? You take the derivative of j, the cost function with respect to w, and move w in that direction. So w gets updated as eta times the gradient of j. Notice that j is the same for all these problems. It's the cross entropy function for classification, and it's the squared error for regression. Now let's look at neural networks, which is what you'll learn about in this course. How do we do prediction? It's the same thing with just one extra step. Actually, it just looks like two logistic regressions in a row. How do we train? Same thing as before. Take the derivative and move in that direction. Keep in mind that we can make our network arbitrarily deep, so you could have W1, W2, W3, and so on. You'll see how we can incorporate any number of weights in this class. So what about convolutional neural networks? Well, to do that, you first need to know about convolution, which isn't really a machine learning thing. It's more of a signal processing thing. Nevertheless, I do go through some examples in my convolutional neural networks course. So how do you do prediction? Well, that's just the same as before, except instead of W2 times X, we have W2 star X, where the star means convolution. As with our regular neural networks, you can have any number of convolutional layers and regular multiplication layers. How do we train this? Exactly the same thing as before. You take the derivative and you move in that direction. You should be seeing a pattern now, hopefully. What about recurrent neural networks? Just like how we introduced one new thing with convolutional neural networks, we'll introduce one new thing here, which is time. In particular, we'll split up the two calculations so you'll see that the first calculation depends on its last value. Pretty simple concept. And if you guess that the way we train these is by taking the derivative of the cost function and going in that direction, you would be correct. The last thing we'll look at is autoencoders. Auto in this case means self. So this is just a neural network where the target variable is the input variable instead of some other target variable. This is an even easier concept than CNNs and RNNs because you can do these using only the knowledge you learned in this course. Just instead of calling train XY, you call train XX. But just because these are really simple doesn't mean they aren't awesome. One big advancement in deep learning was that we learned that you could stack a bunch of autoencoders together, put a logistic regression layer at the end, and get better predictions than just a plain deep neural network. And you can do all that using just the knowledge you learned in this course. So what is the moral of this story? It's that knowing how to take the derivative of the cost function is absolutely critical to deep learning. It's that the things you learn in this course are fundamental to the things you'll learn about later. Does that mean you'll be ready to write your own CNN or RNN today? Probably not. But as you've seen, all they require is the addition of just one more simple step. So by mastering the material in this course, you're making all these other things that might seem out of your reach today just a small step away. Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this class, I'm going to go through some exercises and tell you how you can get good at deep learning. Now, when I first made this course, I made the assumption that the people who want to learn deep learning had some reason for wanting to learn it. Now, I get a lot of questions about, can you put up more exercises? And so I made this lecture to address that question. Deep learning and machine learning models in general are used for making predictions. So what is it you want to predict? What are you interested in? Well, hopefully you can answer that question for yourself. There are a ton of standard machine learning datasets that researchers use for benchmarks that you can work on. They are easy to find and they are free, but they are not as good as things you are passionate about. But you want to look up MNIST, CFAR, SVHN, and the IRIS dataset. You can also look up government data, the Enron emails, and many more. The next thing is that there is no magical homework question that will make you great at deep learning. This isn't really like physics, where I can ask you to calculate the force of a man standing on an elevator. In fact, the more theoretical questions regarding deep learning are very, very hard, so you probably do not want to work on these at this level. The most important thing is to make sure you understand the material already given. As a checklist, I would make sure you are able to do the following by yourself, step by step, without watching the videos. So you should be able to take the derivative of a sigmoid, the hyperbolic tangent, the softmax function. You should be able to take the derivative of the cos with respect to the weights using softmax. This is more challenging than you might think, because while it doesn't require you to learn any new math, it does require you to be very careful with your calculation. Notice that I deliberately left it out for you as an exercise in this course. Next, you want to try to take the derivative of the cost with respect to the weights in a very deep network and make sure that you see and understand the recursive pattern. Next, you want to vectorize the weight update equations so that you can code them like this in NumPy. Now, just to reiterate one more time, predictive models are meant to be used on data. You are the one who has to choose the data to use the techniques on, because only you know what you're interested in. To get good at doing deep learning, you need to practice using these models. It's not just plug and chug. You need to pick the right number of hidden units, the right number of hidden layers, the right learning rate, the right regularization, and so on. It will take lots of time and lots of waiting. You're only going to get good by trying it yourself. If you're trying to get good by watching more videos, that's like trying to learn how to play tennis by reading a book. It doesn't help unless you actually play tennis. If or when you come across an issue, feel free to ask it on the discussion board. You definitely want to inspect the cost function as gradient descent progresses, which is why I always print it out and I make a plot once training is complete. If you see your cost increasing or blowing up, you know something is definitely wrong. When you do practice these exercises, you're going to be forced to answer questions like, what if my data has outliers? Or what if there's missing data? Or how can I process images, sounds, and sentences? Notice that in this class we work with abstract vectors. One common method of pre-processing data is to normalize it in some way, to make all the input values between 0 and 1, or to subtract the mean and divide by the standard deviation. With words and sentences, you can use the bag of words technique, which is just a one-hot encoding of the words, or you could use something more complicated like TF-IDF. You learned about one-hot encoding and some of the more basic general machine learning and data science techniques in my first class, Linear Regression in Python. I've designed these courses so that at each level, the complexity goes up a little bit and the level of hand-holding goes down. This means that at the beginning, you're going to see more verbose code and maybe some math that may not seem very rigorous. As we go to higher levels, we are going to skip more steps and tighten up the code. So to summarize this, how do you get good? Deep learning is a tool. The people who are good with their tools are the people that use their tools all the time.
Hey everyone, and welcome back to this class, Data Science, Deep Learning in Python, Part 1. In this lecture, we are going to look at how you can apply everything you've learned in this course with just 3 lines of code. We know that in the real world, you're not going to be implementing a neural network from scratch every time. That doesn't make sense because for any given problem, the neural network you use is still just a neural network. There isn't one kind of neural network for finance and one kind of neural network for biology. A neural network is just a neural network. This makes a neural network the perfect candidate for being included in a library. A library is code that someone else wrote that you can just download and use. For example, NumPy and Matplotlib are libraries. You use them, but you don't need to write them from scratch every time you use them. If you wanted to study how to optimize matrix and vector operations, then you would try to write your own version of NumPy or maybe parts of it. Similarly, in this course, you are studying deep learning, which is why you are writing neural networks. This is different from just using neural networks, which, as you'll see, is just 3 lines of code. So that's why we didn't just jump straight to this from the beginning. This course is about deep learning itself. It's not a course about reading documentation or using APIs. It would actually be quite an amazing feat if I could talk for 5 hours about just 3 lines of code. So we talked about libraries. There is a library in Python that anyone who is interested in machine learning or data science should know about. That's the scikit-learn library. If you haven't seen it in another course of mine, that's fine. There isn't much to it. To install it, you just need to do sudo pip install -u scikit-learn or sudo easy install -u scikit-learn. The -u is there so that if you already have it, then all it will do is upgrade. I suspect that all of you already know how to install Python libraries, given that you've already had to install some to write the code in this course and in the prerequisites. I believe that version 0.18 is the first version of scikit-learn to include neural networks, so you may want to verify that you have at least this version for the code to work. Now there's a very good reason this course has been structured the way it is. If you recall, the first section was on prediction, and the second section was on training. If you've used scikit-learn before, then you know the corresponding scikit-learn functions are predictx and fitxy. You'll notice that I've alluded to these in the past as well. In fact, every supervised machine learning model in scikit-learn has exactly this same API. So it doesn't matter if you're creating a neural network. You could be creating a logistic regression model or a decision tree. They all have the same interface. So that's our 3 lines of code. Line number 1 is the line where you create the model. Line number 2 is where you fit the model to training data. And line number 3 is where you make predictions on new data. Now, of course, you'll need additional lines to import MLP classifier and load your data, but I'll assume that these are largely trivial to you by now. Note that for regression problems, you would use MLP regressor, which is part of the same module. Not surprisingly, it has the same interface as well. So at this point, you already know a lot about neural networks. You might be wondering, well, how do I choose the learning rate, the number of hidden layers, or the number of hidden units, or the activation function? If you go to the scikit-learn documentation, you'll see that these are all arguments into the constructor. The easiest way to find this page is to Google it, since the URL is long. So you'll notice that there are many more arguments here that you may not have even known existed. But don't worry, we will cover these in Deep Learning Part 2, which is all about improving backpropagation. This course is all about understanding what backpropagation is in the first place. So at this stage, I assume you have no problem reading documentation, and I'm confident you'll be able to parse the information on this page and navigate this website just fine. If you can't, remember that you should use the discussion board to ask questions. Okay, so now I'm going to do a super simple example in code to show you how to use scikit-learn. In fact, this is so simple you probably don't even need me for this. So I assume you already have some data set you're working with at your job or something you're looking at as a hobby. If that's the case, then I would challenge you to go and read the scikit-learn documentation yourself, create an MLP using scikit-learn, plug in your data set, and see what kind of accuracy you get. If you want to look at my code as a comparison, The irrelevant file in the course repo is sklearn.ann.py. So if you go over to sklearn.ann.py, you'll notice that this is a very short file. Most of it is just importing stuff. We want to make use of the e-commerce data again, which is a neighboring folder. So we have to add that folder to the path and then import getData from the process script. Next, we import MLP classifier and shuffle so that we can split the data. Next, we get the data and split it into 70% train and 30% test. Then we create the model as I showed you earlier. I'm overriding some of the default arguments, as you can see. I want 2 hidden layers, each of size 20, and the maximum number of iterations of backpropagation will be 2000. Next, I call the fit function, which is pretty trivial. Yet at the same time, what goes inside the fit function was the hardest part of this course. Finally, I call the score function to get the train and test accuracies and then print them out. Score just calls predict and then calculates how many of the predictions are correct out of the total number of samples passed in, as you would expect. Now let's run this and see what we get. Okay, so everything looks good. Now while this is convenient, there are a couple things to keep in mind. When would you use this? Personally, I would use it whenever I want to do a quick test to see how a neural network would perform on a dataset with a specific setting of hyperparameters. What are some downsides? First, you don't get a plot of the costs at each iteration, so you don't know if the learning rate you chose is too high or too low. This one is huge because I always like to look at a plot of the cost for any iterative algorithm. Second is, even though there are a lot of options in the constructor, it's still not an exhaustive list of options. So if a feature you want isn't implemented, then you can't use it. It's also not great for learning purposes. For learning, you really want to practice writing all the code. The important part of writing code is not the act of writing code itself, but debugging. This is where I see a lot of people fail. It's not about writing 100 or 1000 lines of code. It's about having the skill and patience to diagnose a problem and fix it. This is what differentiates a good data scientist from a run-of-the-mill data scientist. Repetition is key. You'll see that a lot of the code in this course repeats itself. By repeating a pattern, it becomes second nature. This is a skill you want to have. So for on-the-job stuff, go ahead and use scikit-learn. But when it comes to your own learning, you want to implement things and most importantly, debug the problems on your own.